So in the last video, we introduced Kruskal's algorithm for kind of joining these islands of connected components together. But in order to do that, we kind of had this pseudocode that had some operations that we probably don't know how to implement efficiently. In particular, we needed some structure that was able to associate which one of these sub MSTs any particular node is associated to, the find operation. And then we also needed to be able to union them together to combine these two islands into one. And I don't think any of our existing ADTs can do something that really helps us, especially when it comes to unioning two sets. Maybe the finding might be something about a map, but doing both of those operations seems to be kind of tough. So we're going to define a new ADT that does this kind of finding and unioning really well. So this data structure, or this ADT, is going to be called disjoint sets because it's all about managing these kind of subsets that are disjoint, that don't have any overlap. And this kind of ADT is perfect for something like Kruskal's, where we have this kind of separated connected components that we're trying to join together. So in the abstract sense, and remember, ADTs are abstract descriptions. I'm not telling you how to implement this concretely in a data structure. I'm just telling you what operations would we want? How should it behave? So a disjoint sets ADT, we'll think about its state as being a family of sets. So in this kind of partial run of Kruskal's over here, we have three sets that together, the three of them form like a family. And each of these sets are going to be disjoint, meaning that they don't have any overlap. And we're going to have one extra kind of notion that each set has some representative member or some ID, so some way of telling which set is which. So you might imagine that you can label the sets like 1, 2, 3, or another way of implementing that could be always return one of the elements. So for this for this set, you always return the element A to identify that set, B for this one, and E. Both are kind of valid, and we'll kind of talk about both a bit. But in terms of the operations it provides one that we're going to call make set for just building up one of these structures, so we can ignore that for a little bit. But the two key ones are find and union. So finding a value returns the representative for the set it belongs in. So like if we're using the ID, some ID to represent each set or one of the members, it would say, okay, for this vertex, which set does it belong to? And then the ability to union two sets. So combine the sets that contain X and Y into one set. So merging all of them together. So this is the ADT. Now, why are we going to talk about this ADT? Well, it's going to be really helpful on your next programming project, and it's going to be helpful for dealing with Kruskal's. So on project 4, imagine, ignore COVID for a second. You go out for a nice walk, maybe socially distanced if there is COVID, and you find yourself in kind of a labyrinth of a Greek legend, which is kind of a bummer because those things are usually pretty scary. I have some art down here of a Greek depiction of a maze, and I had to put this kind of cute Count Chocula image in front of it because there's a pretty bloody scene in the background. So this is like not your best day finding yourself stuck in this maze. So we're going to want to write an algorithm to help us get out of the maze. So part of your project 4 is, given a maze, how do you solve it? How do you get out? And we're going to essentially, in this project, model the maze as a graph. And then to get out from the starting point to the ending point is in some sense just trying to find the shortest path through the graph. So that might be giving you a hint of what type of algorithm you might want to use to solve the maze. On the second part of the project, we're actually going to have you generate mazes. So how can you make a random maze that you can give to your friends to try to solve? And so what we're going to want in this kind of maze generation algorithm is some way to make sure that we can always connect a path from the start to the end, that guaranteed to connect, and there should only ever be one valid path. We don't want multiple paths. That sounds something like a spanning tree. So one algorithm we're going to talk about for project 4 to generate a generate a maze is a very clever kind of trick. We take some graph that we want, we just choose a graph, and we randomly initialize all the edge weights. Then we find a minimum spanning tree, and the edges that we choose for the minimum spanning tree is going to define kind of what's the path through the maze. So in P4, you're going to implement both of these. You're going to implement Dijkstra's to help solve a maze, and you're going to implement Kruskal's and a disjoint set to help generate new mazes. Now, this project is one of my favorite projects. It's so cool because you get to actually do this kind of cool transformation of graphs to mazes, and it's really fun in the sense that this assignment is very application heavy. Like we have like a graphical user interface that you can like look at the maze being solved and as you generate them. But part of this coolness comes at a bit of a cost. A big learning objective on this assignment is also getting used to working in a larger programming project, right? If you go onto a research project or go into industry, you're going to have to go work on much larger projects. And so there's a lot more starter code for project 4. And part of the reason we're providing so much starter code is because we want to give you practice integrating in an existing code base. So a major part of the challenge in project 4 is actually just reading through the starter code to understand what you need to do and what you need to interface with. Don't underestimate how long it takes to read code. It takes a while to read code and understand what it's doing, and then try to identify how what you're supposed to write fits in. Now, this is designed as a 2-week project because it's actually 2 weeks worth of work. It is never more important to start early. You do not want to find yourself a couple days before the deadline just opening up the project for the first time and not understanding how any of the starter code works. So this is when you want to start early. I put a little asterisk next to the two. We have Thanksgiving in the middle of this project, so you technically have 3 weeks for it, but don't put it off till the end. This is the one project you definitely don't want to put off because it can be really, really tough to kind of understand all the components. So starting that process early is so. So that's kind of my spiel on project 4, kind of what we're doing with these, how we're going to use these disjoint sets and this idea of Kruskal's algorithm to build up mazes. Now, to give you a bit of kind of outline for what we're doing for the rest of kind of today in these videos, is I've described the disjoint set ADT, and just like when we talked about hashing, I want to kind of iteratively develop a solution to this disjoint sets ADT. So I'm going to start building up some data structures that try to solve this problem, and we'll start simple and get more complex. So in this video, we're going to cover in this lecture, we're going to cover the first 3 of these, and then we're going to pick up on Friday where we left off and talk about this 4th and final one, the weighted quick UDing, path compression, all of this stuff. But we'll understand all these terms in a bit. One thing I want to highlight, though, before we kind of go into what all these applications are, is this disjoint sets case study is really, really useful as kind of a metacognitive opportunity. So disjoint sets is a very cool ADT, and we'll see many kind of improvements on our implementations to kind of get to this final one. This is a good chance to, take stock after we talk about each one and understand what is, at a high level, how does it work? What is it trying to do? And how is it different than the last one we talked about? What problem are we trying to solve by adding this new complication or this new aspect of our implementation? What problem was it trying to solve, and did it solve it? Did it make it more efficient? Did it make it work, etc.? So making sure you're pausing and kind of looking back at when we talk about the next implementation of something, comparing it to the previous is really, really important. So I want to start us off with kind of what you might think is your first idea of trying to represent this disjoint sets ADT. So can we use an existing structure that we already do? Which is also the approach of, can we just throw a map at it and hope it works? So what you could do is probably the simplest representation is make a map that maps from like the identifier for each set. So maybe we're saying we label the first set 1, the second set 2, and then we map it to all of the elements that belong to that set. You can make this mapping from ID to all of the elements that belong in that set. So then to find a value, we just go into, to find a value, like say find what set is Eileen in, we have to scan through all of these kind of sets that we're being mapped to and find Eileen. And then we can return the key. And then for unioning, well, we still actually have to figure out which set the two elements are in, and then we have to do the work to combine them. So this implementation ends up being theta of n for pretty much all of the operations. We're not really going to talk about the make set. We're really going to focus on find and union. So that's going to be theta of n for both those operations. And the reason is we don't make it really easy to find what set a particular element belongs in. We associate the mapping to go from set ID to all of the values in it. But it would be kind of nice if we had some kind of instant lookup from the value inside the set into which representative ID belongs to. And so usually whenever you find yourself kind of struggling to like, I wish I was able to like look this thing up, that's a sign of where you might want to use a map. So what if we change this? What if we turn that map around? And so this is going to be our first implementation of the disjoint set structure. We're going to call it QuickFind. The idea is it's still maps, but we reversed it. The keys are going to be the values that the sets will be over, so like the vertices in our graph. And the value that we map to is going to be the representative ID. So instead of saying the set 1 maps to Eileen and Santino, we'll say Eileen maps to 1, Joyce maps to 2, Santino maps to 1, etc. This representation is very, very helpful because it lets us now get instant access to the representative ID for any particular value. So what if you want to find what set Santino's in? Well, we just look it up in the map. We get that O of 1 access if it's a hash map. It says, oh, Santino's in set 1. We can find Ken and say Ken's in set 2. We can then identify whether Ken and Santino are in the same set. We just ask, are Santino and Ken, if we find both of them, do those agree? And since they don't, Santino's in set 1, Ken is in set 2, we know they're in different sets. But, for example, Santino and Eileen are in the same set because they have the same representative ID. So if we can store these keys in some kind of hash map structure that provides us instant access, then our find now gets us this like theta over 1 runtime, which is kind of exactly what we want. However, unioning is still not going to necessarily be efficient, right? So how am I going to union Joyce and Eileen sets together in this thing? Well, I have to go find both of them to figure out Eileen's in set 1 and Joyce is in set 2. But then I need to kind of go through the whole structure and then update everyone to say, oh, set 1 and set 2 have now been combined. So we're still going to run into that theta of n runtime for a QuickFind union. What we're going to talk about in our next video, now we've talked about our first implementation, is I want to talk about trying to speed union up. So in the next video, we're going to introduce the next 2 implementations that are going to try to speed up unioning. But this QuickFind is a very good first step at trying to do this disjoint sets implementation.